Hello everyone, hope you are doing well. In this video, we will be discussing the example problems from the NCERT textbook of Class 12 Chemistry, Chapter 2, Solutions. So the example 2.1, calculate the mole fraction of ethylene glycol, C2H6O2 in a solution containing 20% of C2H6O2 by mass. So here we need to calculate the mole fraction of ethylene glycol. In order to calculate mole fractions, we need to calculate the number of moles in the beginning. So now let us calculate the number of moles of ethylene glycol as well as water. So in the question, they have given that we have 20% of ethylene glycol, that is C2H6O2 by mass in the solution. Which means that we have 20 grams of ethylene glycol in 100 gram of solution. So from this we can calculate the mass of water present in the solution. So therefore, mass of water is 100 minus 20, which is equal to 80 grams. So now let us calculate the moles of ethylene glycol as well as water. Moles of ethylene glycol is equal to its mass divided by molar mass. So mass of C2H6O2 divided by molar mass of C2H6O2. So mass of ethylene glycol is 20 grams and molar mass we have to calculate. It is 2 into atomic mass of carbon, that is 12, plus 6 into atomic mass of hydrogen 1 and 2 into atomic mass of oxygen, that is 16. So we have 20 grams divided by the molar mass of ethylene glycol. When we add up all these, we get 62 grams per mole is the molar mass. Upon solving this, 20 by 62, we get 0.322. So that is the number of moles of ethylene glycol. Now we need to calculate moles of water. So number of moles of water is mass of water divided by molar mass of water. So in the solution we have 80 gram of water and molar mass of water. We have 2 hydrogen and 1 oxygen. So it is 2 plus 16, that's 18 gram per mole. So 80 divided by 18, that is 4.444 moles. So now we shall calculate mole fraction of ethylene glycol. So I'll write mole fraction chi of C2H6O2, that is ethylene glycol, that is equal to moles of ethylene glycol C2H6O2 divided by moles of C2H6O2 plus moles of water. Which is equal to 0.322 divided by 0.322 plus 4.444 is equal to 0.068. So this is the mole fraction of ethylene glycol. Similarly, if we are asked to calculate mole fraction of water, let us see how we can calculate it. Now we shall calculate the mole fraction for water. So chi for water is number of moles of water divided by number of moles of ethylene glycol C2H6O2 plus number of moles of water. So we have number of moles of water, that is 4.444 moles, divided by moles of ethylene glycol 0.322 plus 4.444, and this is equal to 0.932. Also we know that the sum of mole fraction of all the components of the solution is equal to 1. So the other way we can find the mole fraction of water is that, since we have mole fraction of glycol plus mole fraction of water is equal to 1. So mole fraction of water, we can calculate it as 1 minus mole fraction of glycol. This is equal to 1 minus 0.068, which is equal to 0.932. So this is the other way by which we can calculate mole fraction of water. Example 2.2. Calculate the molarity of a solution containing 5 gram of NaOH in 450 ml of solution. So here we need to calculate molarity. So we shall write the formula in the beginning. Molarity is number of moles of the solute per liter of the solution. So it is moles of NaOH here in this question divided by volume of solution in liters. So we need to find the number of moles of NaOH. In order to do that, we need molar mass of NaOH. So we will calculate molar mass first. Molar mass of NaOH is equal to 1 into atomic mass of sodium plus 1 into atomic mass of oxygen plus 1. So we have 23 plus 16 plus 1, that's equal to 40 grams per mole. So mass of NaOH is given, that is 5 gram. So using these two data, now we can calculate moles of NaOH. So moles of sodium hydroxide is mass, that's 5 gram, divided by molar mass is 40 gram per mole. So 5 by 40 grams is equal to 0.125 moles. So this is the number of moles of sodium hydroxide. Now in order to find molarity, we need volume of solution in liter. So but in the question they have given it in terms of milliliters. So we know 1 milliliter is nothing but 10 to the power minus 3 liter. So volume of solution, they have given it as 450 ml. So this is nothing but 450 into 10 to the power minus 3 liter. This is nothing but 0.45 liter. Now let us substitute these values into the formula of molarity. So therefore we have molarity is equal to moles of NaOH, that is 0.125 moles divided by volume of solution in liters, 0.45 liters. So 0.125 divided by 0.45. So the answer is 0.278 mole per liter. Nothing but 0.278 molar is the answer. Calculate molality of 2.5 gram of ethanoic acid, that is CH3 COOH, in 75 gram of benzene. So first of all, let me write the formula here. We need to find molality. So molality is number of moles of solute per kg of the solvent. So moles of solute, that is CH3 COOH here, divided by mass of solvent in kg. So here we have benzene. So C6H6 in kg. So now we will find the number of moles of ethanoic acid and we will substitute into formula. Mass of ethanoic acid is given. So mass of CH3 COOH, that is 2.5 grams, and we have 75 grams, that is mass of benzene. So mass of solvent, that is benzene, is 75 grams. But molality, we are going to express the solvent in terms of kg. So I should divide it by 1000. So I get 0.075 kg. Now in order to calculate moles of ethanoic acid, we require its molar mass. So the molar mass of ethanoic acid formula is given, CH3 COOH. So we have 2 carbon atoms, so 2 into 12, and we have 4 hydrogen atoms, 4 into 1, and we have 2 oxygen atoms, so 2 into 16. So we have 24 plus 4 plus 32. So the molar mass of ethanoic acid is 60 grams per mole. Now we shall calculate moles of ethanoic acid. So moles of CH3 COOH is equal to its mass by molar mass. So mass is 2.5 grams. Molar mass is 60 grams per mole. So 2.5 divided by 60, that gives us 0.0417 moles. We will substitute the number of moles of ethanoic acid and mass of benzene in terms of kg, and we will find molality. Therefore, molality is equal to number of moles of ethanoic acid. It is 0.0417 moles divided by mass of benzene in kg, 0.075 kg. So the molality is 0.0417 divided by 0.075, and this is equal to 0.556 mole per kg. Nothing but this is the molality of the solution. Example 2.4. If nitrogen gas is bubbled through water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water? Assume that nitrogen gas exerts a partial pressure of 0.987 bar. Given that Henry's law constant for nitrogen at 293 Kelvin is 76.48 kilobar. So here we need to find the number of millimoles of nitrogen gas that is dissolved in 1 liter of water. So they have given us Henry's law constant and partial pressure of nitrogen gas. So here we shall make use of Henry's law, that is the expression P is equal to KH into chi. So in order to find the number of moles, first of all we will calculate the mole fraction. Then using that we can calculate the number of moles. So they have given us partial pressure for nitrogen 0.987 bar. Also they have given us Henry's law constant KH, and that is equal to 76.48 kilobar. So this kilo means 10 to the power 3. So this is equal to 76.48 into 10 to the power 3 bar, which is equal to 76480 bars. So using these two, we can find the mole fraction for nitrogen. So chi for N2 we can calculate. So if I just rearrange the formula for Henry's law constant, chi of N2 is equal to P divided by KH. That P is 0.987 bar and KH is 76480 bars. So this is equal to 1.29 into 10 to the power minus 5. We have obtained mole fraction for nitrogen. Now we know the other formula for mole fraction is in terms of number of moles. So we have number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of water, since the nitrogen is passed through water. We shall calculate the number of moles of water. So here in this formula, number of moles of nitrogen is what we have to calculate and number of moles of water we will find now. So N of H2O is nothing but mass of water divided by the molar mass of water. So they have given us nitrogen gas is dissolved in 1 liter of water. So they have given us volume of water. Now if volume is known, we can calculate the mass. Correct? How? So in case of water, at standard temperature and pressure, it's considered that water's density is 1 gram per ml. So therefore, mass of water and volume of water are equal. So therefore, I can consider mass of water is 1000 grams divided by its molar mass, that is 18 gram per mole. So 1000 divided by 18 gives us number of moles of water. It is 55.5 moles. Now let us substitute this into the formula for mole fraction of nitrogen. We have calculated the mole fraction is 1.29 into 10 to the power minus 5. Number of moles of nitrogen is what we have to calculate. In the denominator also, number of moles of nitrogen plus number of moles of water, that is 55.5 moles. So if we consider the number of moles of hydrogen with respect to the number of moles of water, this is very less than 55.5. So therefore, denominator I can write it as number of moles of nitrogen divided by 55.5. So this is because since number of moles of nitrogen is very less than 55.5. So we have 1.29 into 10 to the power minus 5 is equal to number of moles of nitrogen divided by 55.5. Now we will simplify this. Number of moles of nitrogen is equal to 1.29 into 10 to the power minus 5 into 55.5. This is equal to 7.16 into 10 to the power minus 4 moles. So we have found out the number of moles of nitrogen. But in the question, they have asked us to find the number of millimoles of nitrogen that is dissolved. So we have 1 millimole is nothing but it is 10 to the power minus 3 moles. So now here we have 7.16 into 10 to the power minus 4 moles. So how many moles, millimoles does we have? We just have to cross multiply. This is equal to 7.16 into 10 to the power minus 4 mole into 1 millimole divided by 10 to the power minus 3 moles. So moles and moles gets cancelled. Just by simplifying the numerical values, we get 0.716. And this is the number of millimoles of nitrogen. And therefore, the answer is 0.716 millimoles. Example 2.5. Vapor pressure of chloroform CHCl3 and dichloromethane CH2 at 298 Kelvin are 200 mmHg and 415 mmHg respectively. Calculate the vapor pressure of the solution prepared by mixing 25.5 gram of CHCl3 and 40 gram of CH2Cl2 at 298 Kelvin, and calculate mole fractions of each component in vapor phase. So here we shall make use of Raoult's law and the expressions related to it. So first of all, we need to calculate the vapor pressure of the solution. So in order to calculate that, here we have to find the mole fractions, right? I will make use of the expressions from Raoult's law, that is P is equal to P naught chi. So this is the expression that we are going to use. Then in order to find the total vapor pressure, since we have two components, that is chloroform and chloromethane, we will be finding P1 is equal to P1 naught chi 1 and P2 is equal to P2 naught chi 2. Then to find total vapor pressure, we will add both. P total is equal to P1 plus P2 we will do. So in order to find P1 and P2, first of all, let us calculate the mole fractions of 1 and 2. In order to do that, we need to find the number of moles. So here, the component 1 is nothing but I'll consider it as chloroform. So this is component 1 is chloroform, and 2 means I represent dichloromethane, that is CH2Cl2. So this would avoid a lot of confusions. Okay. Now they have given us the masses. Okay. So I'll write M1 is mass of chloroform. It is 25.5 gram. And mass of dichloromethane, I'll write it as M2, that is equal to 40 grams. Molar mass of dichloromethane, CH2Cl2, let me write this as M2, that is equal to 1 carbon atom plus 2 hydrogen, 2 chlorine atom. So 2 into 35.5, and that is equal to 85 grams per mole. Similarly, molar mass of chloroform, CH3Cl3, since it is taken as component 1, so M1, that is equal to 1 into 12 plus 1 into 1 plus 3 into 35.5, and that is equal to 119.5 gram per mole. So now let us find the number of moles of chloroform and dichloromethane. So N1 is the number of moles of chloroform, that is M1 by M1, which is equal to 25.5 grams divided by 119.5 grams per mole, and this is equal to 0.213 moles. Similarly, number of moles of dichloromethane, N2 is M2 divided by M2, which is equal to 40 divided by 85. So 40 by 85 is 0.47 moles. Now we shall calculate the mole fractions of dichloromethane as well as chloroform. Mole fraction of chloroform chi 1 is N1 divided by N1 plus N2. So N1 here is 0.213 divided by 0.213 plus 0.47. And this is equal to 0.312. Similarly, the mole fraction of dichloromethane, I can calculate it by subtracting the mole fraction of chloroform from 1. So 1 minus 0.312, and that is equal to 0.688. Or the other way you can do is using the number of moles. Chi 2 is equal to N2 divided by N1 plus N2 you can do. You will get the same answer. It is 0.688. After this step, you can solve the question by two ways. Either, as I mentioned in the beginning, that is to find P1 and P2, and then to find P total, you have to add P1 and P2. Or the other method is to use the formula P total is equal to P1 naught plus P2 naught minus P1 naught into chi2. Either of the ways you can solve it. So first I will solve by this particular method, and later on I will use the second method and I will solve the question. So now using the first question, we need to find P1 and P2. So P1 is the pressure corresponding to the chloroform. So the formula I have to write is P1 is equal to P1 naught into chi1. So P1 naught, that is given to us, it is 200 mmHg. So chi1 naught is just now we have calculated 0.312. So P1 is 200 into 0.312, and that is equal to 62.4 mmHg. Similarly, I can calculate P2, that is equal to P2 naught into chi2. So P2 naught we have is 147.9 mmHg into the value of chi, that is 0.688, and the answer we are going to get here is 285.5 mmHg. So now I can write P total is equal to P1 plus P2, and this is equal to 62.4 mmHg plus 285.5 mmHg, and this is equal to 347.9 mmHg. So this is one way how we can arrive at the answer, or the second way, as I told, to use the formula P total is equal to P1 naught plus P2 naught minus P1 naught into chi2. Now let me use this particular equation. Now let me substitute all the values into the expression. So we have P total is equal to P1 naught, that is 200 mmHg, plus P2 naught 415 minus P1 naught is 200 into chi2, that is 0.688, which is the mole fraction of dichloromethane. So simplifying this, we get 200 plus 147.9, and this is equal to 347.9 mmHg. So this is how you can answer first part of the question. Now moving to solve the second part. That is, we are asked to find mole fractions of each components in their vapor phase. So for this, we are going to use the expression P1 is equal to Y1 into P total. So here P1 is what we have calculated just in the previous, okay, using Raoult's law. Y1 is representing mole fraction of the components in their vapor phase. So this is for chloroform. Similarly, for dichloromethane, it is P2 into Y2 into P total. We have just calculated P1 and P2. So P1 is 62.4 mmHg and P2 is 285.5 mmHg. So now we shall substitute these values into equation 1 and equation 2. Also we have calculated P total, that is equal to 347.9 mmHg. So now in the vapor phase we can calculate the mole fractions. So I can write Y1 is equal to P1 divided by P total, which is equal to P1 is 62.4 mmHg divided by P total, that is 347.9 m. After simplifying this, we get the value of mole fraction of chloroform in its vapor phase, that is 0.18. Similarly, to calculate mole fraction of dichloromethane in the vapor phase, we can make use of equation 2. So from equation 2, I can write Y2 is P2 divided by P total. P2 is 285.5 mmHg divided by P total, that is 347.9 mmHg. Simplifying this, we get the mole fraction of dichloromethane as 0.82 in its vapor phase. And this is how you can answer second part of the question. Example 2.6. The vapor pressure of pure benzene at certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram when added to 39 gram of benzene, whose molar mass is 78 gram per mole. Vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid substance? So here we are asked to find molar mass of the solute that we are adding. So let us list what are the things that is given in the question. So they told vapor pressure of pure benzene is 0.850 bar. So for pure benzene, pure solvent it is. So I can write it as P1 naught, that is 0.850 bar. So non-volatile, non-electrolyte solid weighing 0.5 gram is added. Means they are telling about mass of solute. So that is written as W2, which is 0.5 gram. When added to 39 gram of benzene. So benzene, its weight, let me consider it as W1, that is 39 gram. Molar mass of benzene is given. So capital letter M1, 78 grams per mole. Vapor pressure of the solution then decreases to 0.845 bar. So vapor pressure of the solution they have given. So let me denote this as P1, that is equal to 0.845 bar. Now they have asked us to calculate molar mass of the solid substance. Means M2 is what we have to calculate. Here we observe that after adding the solute, vapor pressure of the solution has been decreased. So here we can make use of the formula of relative lowering of vapor pressure. So I can write P1 naught minus P1 divided by P1 naught is equal to W2 into M1 divided by M2 into W1. So M2 is what we have to calculate. Let us substitute all other values. P1 naught is 0.850 minus P1 is 0.845 divided by 0.850, that is equal to W2, which is 0.5 grams into M1, that is 78 grams per mole, divided by M2 is what we have to calculate and multiplied by W1, that is 39 grams. So after simplifying this, we get the value of M2 as 170 grams per mole. So the molar mass of the solute is 170 gram per mole. Example 2.7. 18 gram of glucose C6H12O6 is dissolved in 1 kg of water in a saucepan. At what temperature will water boil at 1.013 bar? Kb for water is 0.52 Kelvin kg per mole. So in the question, they have asked us to find the temperature of the solution after adding 18 gram of glucose to 1 kg of water. So in order to find that temperature, we need to find what is the increase in the temperature, means the boiling point that has occurred after the addition of glucose. So first of all, we need to find the elevation in the boiling point. So in order to find the elevation in boiling point, we have to find molality of the solution. So we know molality is moles of solute. So that is glucose here, divided by mass of solvent in kg, that is mass of water in kg. In order to calculate number of moles of glucose, we will calculate molar mass of glucose. So molar mass of glucose, that is C6H12O6, is 6 into 12 plus 12 into 1 plus 6 into 16. So after solving this, we get molar mass of glucose as 180 grams per mole. Now, mass of glucose is required. So they have given it in the question. Mass of glucose is equal to 18 grams. So we can calculate number of moles of glucose. So moles of glucose is equal to its mass, that is 18 gram, divided by molar mass, that is 180 grams per mole. Simplifying this, 18 divided by 180, we get 0.1 moles. So we have calculated number of moles of glucose. Now we need mass of water in kg. So they have already told us we have 1 kg of water. So we can calculate molality. Molality M is equal to moles of solute, that is glucose, 0.1 mole, divided by mass of water in kg, that is 1 kg. And therefore, the molality is 0.1 mole per kg. So delta TB is equal to, it is Kb into molality. Molar elevation constant Kb for water is 0.52 Kelvin kg per mole. And molality we have calculated just now, it is 0.1 mole per kg. So let us simplify the units. Moles and kgs terms get cancelled. We are left with Kelvin. So we have to multiply 0.52 with 0.1 to get the change in the temperature after adding glucose. It is 0.52 into 0.1, which is 0.052 Kelvin. So this is the change in the temperature that is observed after adding glucose. At 1.013 bar pressure, water boils at 100 degrees centigrade. That is 373.15 Kelvin in terms of Kelvin. So, boiling point of solution is 173.15 Kelvin plus the change in temperature that we have observed. It is 0.052 Kelvin. Adding these two values, we get the boiling point of the solution. So it is 373.202 Kelvin. Example 2.8. The boiling point of benzene is 353.23 Kelvin. When 1.80 gram of a non-volatile solute was dissolved in 90 gram of benzene, the boiling point is raised to 354.11 Kelvin. Calculate the molar mass of the solute. Kb for benzene is 2.53 Kelvin kg per mole. So here, after adding the solute, the boiling point of benzene has been increased. So the elevation in boiling point we shall calculate. Delta Tb is the difference between 354.11 Kelvin and 353.23 Kelvin. This is equal to 0.88 Kelvin. So here they have asked to find us the molar mass of solute. So let me consider the solute as 2. So the molar mass of solute is M2. Let us list the other data that is given in the question. So they have told the non-volatile solute was dissolved in benzene. So they have told 1.80 gram of non-volatile solute is dissolved. So this is W2. And they have given us mass of benzene, that is 90 gram. So that's W1. Boiling point is rise to 354.11 Kelvin. They have asked us to calculate molar mass of solute, means M2 we have to calculate. They have given us the value of Kb 2.53 Kelvin kg per mole. We have the formula M2 is equal to 1000 into W2 into Kb divided by delta Tb into W1. Let us substitute all the data into the formula to calculate molar mass of the solute. 1000 into W2, that is 1.80, Kb is 2.53 divided by delta Tb, the elevation in the boiling point, 0.88 into W1, that is 90 grams. After solving, we will get molar mass of the solute as 58 grams per mole. Example 2.9. 45 gram of ethylene glycol is mixed with 600 gram of water. Calculate the freezing point depression and B, freezing point of the solution. In A, we have to calculate the depression in freezing point, that is delta TF. So in the question they have given us mass of ethylene glycol, that is 45 gram, and they have also given us mass of water, that is equal to 600 grams. Now we know that delta TF is related to molality. So delta TF is equal to Kf into molality, where Kf is molar depression constant, and for water the value of Kf is 1.86 Kelvin kg per mole. So now we shall find molality. So molality of the solution is equal to moles of solute divided by mass of solvent in kg. So we need to calculate moles of ethylene glycol. So it is its mass by molar mass. So mass is 45 grams. Molar mass we will calculate. So 2 into 12 plus 6 into 1 plus 2 into 16 gram per mole divided by mass of solvent in kg. So we have mass of solvent in terms of gram, that is 600 gram. We need to convert this into kg. We have to divide it by 1000. So we have 0.6 kg of the solvent. So mass of the solvent is 0.6 kg. So 45 grams divided by molar mass of ethylene glycol, that is 62 grams per mole, divided by 0.6 kg. 45 divided by 62 is 0.73 moles divided by 0.6 kg. So dividing 0.73 by 0.6, we get molality of the solution, that is 1.2 mole per kg. Now substituting the molality into the formula of depression in freezing point. Delta TF is equal to 1.86 Kelvin kg per mole into 1.2 mole per kg. So we have 1.86 Kelvin into 1.2 and this is equal to 2.2 Kelvin. So this is the decrease in the freezing point that is observed after adding the solute, that is ethylene glycol, to 600 gram of water. Now answering question B, that is we should be telling what is the freezing point of the solution. So freezing point of the solution is the difference between normal freezing point and the change in the freezing point that is observed. So 273.15 Kelvin minus 2.2 Kelvin, and that is equal to 270.95 Kelvin. Example 2.10. 1 gram of a non-electrolyte solution dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.40 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin kg per mole. Find the molar mass of solute. So we will list the data that is given. They are telling that 1 gram of non-electrolyte solution. So solute, its mass W2, that is 1 gram. It is dissolved in 50 gram of benzene. Weight of solvent is given W1, that is 50 gram. It lowered the freezing point of benzene by 0.40 K. Depression in the freezing point is 0.40 Kelvin. The freezing point depression constant of benzene is, means they have given the value of Kf 5.12 Kelvin kg per mole, and we are asked to find the molar mass of the solute. Molar mass of the solute M2 is what we need to calculate. We have the expression M2 is equal to Kf into W2 into 1000 divided by delta TF into W1. We will substitute all the data into this particular formula and we will calculate molar mass of the solute. So Kf is 5.12, W2 is 1 into 1000 divided by delta TF, that is 0.40, into W1, that is 50. After solving this, we will get molar mass of the solute, and that is equal to 256 gram per mole. Example 2.11. 200 centimeter cube of an aqueous solution of a protein contains 1.26 gram of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 to the power minus 3 bar. Calculate the molar mass of the protein. So here we need to calculate molar mass of the protein and we are provided with osmotic pressure. We have relation between the molar mass of the solute and osmotic pressure, that is M2 is equal to W2 into R into T divided by osmotic pressure pi into V. We will list the various quantities that is given to us in the question. So we have volume of aqueous solution V, that is 200 cm cube or 200 ml. This should be in terms of liter. So we have to divide it by 1000. So in terms of liter, we have 0.2 liter of the solution. And we are provided with temperature T, that is 300 Kelvin. And we know the value of R, that is 0.083 liter bar per mole Kelvin. Let us substitute all these values into the formula. So we have M2 is equal to W2. Sorry, I forgot to mention it. Weight of solute, that is given 1.26 gram of protein. So W2 is 1.26 into R 0.083 into the temperature 300 Kelvin divided by osmotic pressure. So I did not include that too. So pi osmotic pressure is 2.57 into 10 to the power minus 3 bar. So it is 2.57 into 10 to the power minus 3 into volume. It's 0.2 liter. Let us simplify this and solve. We will find the answer as 61,022 grams per mole as the molar mass of the protein. Example 2.12. 2 gram of benzoic acid dissolved in 25 gram of benzene shows a depression in freezing point equal to 1.62 Kelvin. Molal depression constant for benzene is 4.9 Kelvin kg per mole. What is the percentage association of acid if it forms dimer in the solution? Let us list what are the data that is given to us in the question. So they have given us mass of benzoic acid. So that is W2 is equal to 2 gram. Dissolved in 25 gram of benzene. So W1 is 25 grams. Shows a depression in freezing point equal to 1.62 Kelvin. So delta TF is given to us 1.62 Kelvin. The molar depression constant for benzene is 4.9 Kelvin kg per mole. So the value of Kf is 4.9 Kelvin kg per mole. What is the percentage association of acid? So we need to calculate percentage association. In order to do that, in the beginning, we shall calculate what is the molar mass of benzoic acid. Its normal molar mass as well as what is the molar mass that is observed with respect to the solution that is given to us. Using all these data, we can calculate the molar mass of benzoic acid, that is M2 is equal to Kf into W2 into 1000 divided by delta TF into W1. Substituting the values, Kf is 4.9, W2 is 2 into 1000 divided by 1.62 into 25. And this is equal to 241.98 gram per mole. So now this is the observed molar mass of benzoic acid. That is equal to 241.98 gram per mole. The actual molar mass we shall calculate now. So the formula for benzoic acid is C6 H5 COOH. So we have 6 carbon atoms, 6 hydrogen atoms and 2 oxygen atoms. So the molar mass is 122 gram per mole. So we observe the abnormality in the molar mass when it is added to benzene. Now we shall see what happens when benzoic acid is added to benzene. How does it react? Benzoic acid undergo association when it is added in benzene. So that is written as C6H5 COOH giving C6H5 COOH 2 times. Means a dimer of benzoic acid is formed here. Let me balance the equation by writing 2 here. Initially, at the time t is equal to 0, we will consider we have 1 mole of benzoic acid. means 1 into 1. So totally 2 moles of benzoic acid is there. So the dimer will not be formed. So at the time 0, concentration of dimer will be 0. Later on, we shall consider that alpha moles of dimer is formed. So meanwhile, the concentration of benzoic acid would be 1 minus alpha moles. So since we have 2 moles of benzoic acid here, the concentration would be 2 into 1 minus alpha moles. So if I consider this concentration as 1 minus alpha mole, then the concentration of dimer would be alpha divided by 2 moles. So an equilibrium will be established at this stage. So when time t is equilibrium, we have 1 minus alpha moles of benzoic acid which is undergoing association and forming alpha by 2 moles of dimer. So now at equilibrium, I can write the total number of moles of particles. That is nothing but it is sum of 1 minus alpha and alpha by 2. So we have 1 minus alpha plus alpha by 2. This is equal to 1 minus alpha by 2. So this alpha itself is considered as the degree of association. Now this total number of moles of particles is equal to Van 't Hoff's factor. Total number of particles at equilibrium is equal to Van 't Hoff's factor, which is denoted by I. And that I is nothing but it is ratio of normal molar mass to abnormal molar mass. The number of moles of particles at equilibrium is 1 minus alpha by 2. And this 1 minus alpha by 2 is equal to normal molar mass, which is 122 grams per mole, divided by the abnormal molar mass, which is 241.98 gram per mole. We will simplify this. 1 minus alpha by 2 is equal to 0.504. So I can write alpha by 2 is equal to 1 minus 0.504. Alpha by 2 is equal to 0.496, and therefore alpha is equal to 0.496 into 2, and that is equal to 0.992. And therefore we can tell that the degree of association of benzoic acid in benzene is equal to 0.992 into 100. That is equal to 99.2%. Example 2.13. 0.6 ml of acetic acid CH3 COOH having density 1.06 gram per ml is dissolved in 1 liter of water. The depression in freezing point observed for this strength of acid was 0.0205 degrees centigrade. Calculate the Van 't Hoff factor and the dissociation constant for acid. So in the question they have given us the observed freezing point. Now from the given data we shall calculate the depression that is observed in the freezing point, and ratio of both will give us Van 't Hoff factor. So we know the relation delta TF is equal to KF into M, where M is molality. So we need to calculate molality of the solution in the beginning. Molality is is equal to moles of acetic acid divided by mass of solvent in kg. So mass of solvent, that is water here. We shall calculate moles of acetic acid. So moles of acetic acid is equal to its mass by molar mass. We are not provided with mass of acetic acid directly, but they have given us volume of acetic acid as well as they have given us density. So if we multiply volume and density, we will get the mass. So it is 0.6 ml into 1.06 gram per ml divided by molar mass. We have 2 carbon atoms, so 2 into 12 plus 4 hydrogen atoms and 2 oxygen atoms. Simplifying this, 0.636 gram divided by 60 gram per mole. This is equal to 0.0106 moles. Now let us substitute this into the formula for molality. Molality is equal to number of moles of acetic acid, that is 0.0106 mole, divided by mass of solvent in kg. So here they have given us, we have 1 liter of water. So volume of water is given, that is 1 liter. So since density of water is 1 gram per ml, mass of water is 1 kg. Therefore, divided by 1 kg. So we have 0.0106 mole per kg, that is molality of the solution. Now let us find delta TF, which is Kf into m. The value of molar depression constant, that is Kf, for water is 1.86 Kelvin kg per mole, and molality is 0.0106 mole per kg. After simplifying, we get the answer 0.0197 Kelvin. So this is the depression in the freezing point which we have calculated, but they have given that the depression in freezing point observed was 0.0205 degrees centigrade. Let us calculate the Van 't Hoff factor. Here, Van 't Hoff factor I is equal to observed freezing point divided by calculated freezing point. So the observed freezing point is 0.0205. It is same in terms of centigrade as well as Kelvin. And the calculated freezing point is 0.0197 Kelvin. So ratio of these two gives us Van 't Hoff factor, that is 1.041. Now coming to the calculation of dissociation constant for acetic acid. So we shall write the equation corresponding to that. CH3 COOH, acetic acid, is a weak acid. When it undergoes dissociation, we get CH3 COO minus and H plus. So at the time T is equal to 0, if we have 1 mole of acetic acid, initially no dissociation will take place. So concentration of both the ions will be 0. So once equilibrium is reached, say let us consider alpha moles of ions are getting formed, and this alpha itself is the degree of dissociation of acetic acid. then this is at equilibrium. Then the concentration of acetic acid will be 1 minus alpha. Thus, we can calculate total moles of particles present during equilibrium is 1 minus alpha plus alpha plus alpha. So plus alpha minus alpha get cancelled and we have 1 plus alpha. Now this number of moles of particle are equal to Van 't Hoff factor. So I is equal to 1 plus alpha. The solution is similar to that of the previous example which we have studied. So Van 't Hoff factor is equal to number of moles of particles present at equilibrium. So just now we have calculated I is 1.041 which is equal to 1 plus alpha. From this we can write alpha is 1.041 minus 1 which is equal to 0.041. So this gives us the degree of dissociation of acetic acid and that is 0.041. So this is degree of dissociation of acetic acid. Now we need to determine the dissociation constant for acetic acid. Acetic acid dissociates into CH3 COOH minus and H plus ions. So from this equation I can write dissociation constant is concentration of CH3 COOH minus multiplied by concentration of H plus divided by concentration of acetic acid. Initially, if we have n moles of acetic acid, concentration of ions initially will be 0, but at equilibrium, alpha moles of ions will be formed and we will have n into 1 minus alpha moles of acetic acid. So here we will have n alpha moles of CH3 COOH minus and H plus ions. Now writing concentrations, CH3 COOH minus, its concentration is n into alpha. So the value of n we have calculated, it is 0.0106, that is the moles of acetic acid itself, into alpha is 0.041. This is equal to 4.346 into 10 to the power minus 4. Similarly, the concentration of H plus ions is also n alpha and this is also equal to 4.346 into 10 to the power minus 4. The concentration of acetic acid CH3 COOH is equal to n into 1 minus alpha. This is equal to n into 1 minus 0.041. That is equal to 0.0106 into 0.959, which is equal to 0.0101. Now let us substitute all these values into the expression of dissociation constant Ka. So Ka is equal to concentration of CH3 COOH minus ion 4.346 into 10 to the power minus 4 into concentration of H plus ion 4.346 into 10 to the power minus 4 divided by concentration of acetic acid, that is 0.0101. After simplifying this, we will get the value of Ka as 1.87 into 10 to the power minus 5. In this video, we have completed our discussion on the example problems that is given in the NCERT textbook of Class 12, Chapter 2 Solutions. If you have not watched our videos on NCERT classes, you can watch them by clicking on the playlist here. Thank you for watching. Stay connected and keep learning.